Okay, so I'm audible.
Yes, sir.
Okay, so let me see that in screen. You sent me some question. I did not gone through all of this. First two or three I will solve today, and rest of the question I will solve in next class.
Okay.
So is it visible?
Yes, sir.
Okay. So today I'll solve some question from assignment as well, and few question you sent me, and two or three question left in last class I did not able to solve. So that question I will also solve today. Okay. So let me start with first writing the question, then I will solve. So the van der Waal, okay, van der Waals constant A and B of CO2 are 3.64 liter square bar mole inverse and 0.04 liter mole inverse respectively. Okay. The value of R is, anyway, this we have to remember, 0.082, but here it is given as 0.083. Okay, in bar, decimeter cube, mole inverse, Kelvin inverse. If 1 mole of CO2 is confirmed, oh sorry, no, is confined to a volume of 0.15 liter at 300 Kelvin, then the pressure in bar exerted by the gas. Okay, so what they have asked, van der Waal constants are given, A and B, these are the van der Waal constant, okay, for CO2. which are these values. Okay, the value of R is also known. Now, if 1 mole of carbon dioxide is confined to a volume of this 0.15 liter at 300 Kelvin, the pressure we have to find out. Okay, this is just pure calculation. We know for what is the Van der Waals equation, that for 1 mole of gas, Van der Waals gas, this is our equation, right? So now this A and B are the Van der Waals constant. This A and B are the Van der Waals constant. These values are given. These A and B values are given. Uh, what will be the unit of A and B? How you can find out that unit? This is very trivial, but still, that A by V square should have the same unit of P. Otherwise, you can add only the uh, same quantities, right? You can't add pressure with volume, or this thing, right? But when you are adding two things, then that must have the same unit or same dimension. That means that must be the same quantity. So A by V square should have the unit of pressure. So now, so A by V square should have the unit bar. As here all pressure has the unit of bar. So that's why bar. Okay. So that means A should have unit of bar, and volume. Here volume is liter. So let me write it. Okay. U- Unit of A should be bar into liter square. Bar into liter square. But you have to keep in mind that this is not the original formula. The original formula, there is a n. There is a n. Because it is for 1 mole, that's why we have removed that n. We have put n equals to 1. But in case of unit analysis, we have to consider that n. So, so here will be 1 mole. This is okay. Sorry, no. This is the formula. This is the formula. That's why the mole inverse will be there. N is there, and here will be mole inverse. Now it's correct. Okay. Now you can check the formula: liter square bar mole inverse. Okay. Here, no, this is wrong. Okay, there is a typo, I think, in the question. This should not be mole. This should be mole to the power -2. Otherwise, the unit will not be matched. Yes, because the formula is n square eventually. Because we can write it like, because I have remembered this form. V bar is there, where V bar is actually molar volume. Okay, so molar volume essentially is V by N. So that means V and N should have the same power. Otherwise, you can't write that in terms of molar volume. So it must be N square. Okay. That means it should be this. I think that is a typo. Okay. Now, and here is this. This is NB. This is NB. Okay. This is NB, and here eventually there will be NRP. This is the general formula. Okay. Similarly, what will be the here? N is 1. So similarly, what will be the unit of B? NB should have the unit of volume, means liter. So B should have the unit of liter mole inverse. Okay, now it's consistent. Okay, these values are given. What is A? A is given as 3.64 liter square mole to the power -2 and bar. What is B? B is 0.04 liter mole inverse. Now we have to just calculate the pressure, right? So P plus A by V square into V minus B is eventually RT. R is also given. T is known. B is also known. Okay. So what will be the formula then? P equals to RT by V minus B minus A by V square. You can directly write it. Now what is R? R is 0.083. And what is the unit? Bar decimeter cube. Okay. And we have already discussed in one class that 1 decimeter cube is eventually the 1 liter. Okay, so we can directly write decimeter cube as the liter. Okay, mole inverse, Kelvin inverse into T, which is eventually 300 Kelvin divided by V minus B. V is 0.15, and what is B? 0.04. Okay, and what will be the unit? This is for 1 mole. Mm, okay, so it will be just liter. Okay, now minus A by V square. A has the unit 3.64. Unit is liter square. Mole inverse, that will be not there. Liter square bar divided by V square, 0.15 square liter square. Okay, so this will be, so hard, right, left liter down away. This mole inverse will not be there because number of, oh, let me write it even then, because this is for one mole. Okay, that's why I was not writing. Write it explicitly. You, if you write, then you have to write in each cases. If you want to want to carry the mole, otherwise you have to remove it from everywhere. Then you have to also write it here. Yeah, here will be also mole inverse to, okay, we are writing, so it will be, so cancel out. So eventually it is 0.083 to 300 divided by 0.11 bar minus, again little, you can see it will be 3.64 divided by bar. Now let me calculate it. Divided by 0.11 is 226.36 bar minus 3.64 divided by 0.15 square. It is eventually minus 161.77 bar. Okay, that's correct. Now if you want me to subtract that, it is eventually the, okay, 64.582 bar. Okay, so this is our answer. Let me check that whether the recording is going on or not. Yes, yes, okay. Okay, so now going to question number 2. Okay, where is our question number 2? Hmm. Okay, consider a very simple gas. Okay, made up of two identical particles. Suppose that each particle can be in one of the three possible quantum states. In case of FD statistics, what will be the probability of having both particles in the same state? Okay. So they are asking that very simple gas, two identical particles. You can think like H2, two identical particles made both at the edge. So like that, like this. Suppose that each particle can be in the okay, no, different. Okay, okay. Suppose that each particle can be in one of the three possible quantum states. Okay. In case of Fermi-Dirac statistics, what will be the probability of having both particles in the same state? Okay, means there is a gas, very simple gas means very dilute gas. Okay, uh, having only two molecules or two atoms, you don't know, but two particles are there, only that. Now, that particles are essentially following the Fermi-Dirac statistics, means the particles are fermion. Now, what will be the probability of having both particles in the same state? There are how many energy levels are there? Um, Three possible quantum states. So you have two particles, let's say this and this, because these are Fermi-Dirac particle. That means these are quantum mechanical particles. So you can't distinguish these particles. And there are three essential energy levels. Now, what will be the probability of having both particles in the same energy level? This is very theoretical, basic question, even we can say. We know for
Excuse
fermions,
me, sir.
yes,
Here it is a simple gas made up of two different particles. Can we say that
no,
these
not different, two
two,
identical particles.
two are identical particles? So the same kind of molecules are there.
Yes, same kind of molecule. Identical means, let's say, when you are taking a gas, it may be hydrogen gas, it may be oxygen gas, but when you are considering only one kind of gas, that means each particles of that gas are identical. Okay,
It is
you can't
difficult to
differentiate
understand.
between two oxygen molecules, right? Can you? Is it clear?
Yes, sir. Yes, sir.
Okay. But now that one question may be there, whether that particle will be fermion or boson, that you can't know. Only if the species is known, what gas is this, if it is hydrogen or oxygen, then you can estimate what will be the statistics that particle will be followed. Okay, if that particles are bosonic particles, then obviously they will follow the B statistics. If they are fermions, then FD statistics. So here it is provided that particles are fermions, and we know for fermions there is a restriction, that Pauli exclusion principle. Okay, that which means that a same energy level can't be shared by two particles. This is the Pauli exclusion principle, we know. So that's why in a particular energy level, more than one particle can't be reside. Maximum zero or one. This is a beautiful features of fermionic particle, um, which is not present in the bosonic case. It essentially means the repulsion between two particles. In case of boson, there is nothing, no restriction is there. In only one single energy level, all bosonic particle can be accumulated. But in case of fermions, eventually the Pauli exclusion principle actually provides to be in the same energy state of two particles. That's why two particle in same energy state it's not possible. So eventually the probability will be zero. So this question is not a numerical question. This is totally a conceptual question. So eventually the probability will be zero. Okay. Now question number 3. This question you send me. What is the value of CV of SO3 gas in terms of R? Okay. How does SO3 looks like? SO3. So if you 3s2 CP4, probably this will be the hybridization, and oxygen. So one will be unpaired. Oh, SO3, right? So two will be this. So sp2 means these oxygen are there. So eventually this will be the structure. Okay. So this is the SO3. sp2 hybridized. This is that means a planar structure. And just for curiosity, what will be the point group? There is a C3, V, and B. So it eventually D3H. Okay. Okay. So that's not our business here. They have asked the CV. We know, no, we know that CV is del U del T at constant volume. Now, what is the del U? Sorry, what is the U? U is our internal energy. So that we can write as E translational plus E rotational plus E vibrational. Correct? So now what will be E translational? We know that E equals to number of modes into energy per mode, energy of each mode, right? So number of modes for translational, how much? Three. Sorry, uh, three modes will be there. Yes, correct. And energy for each mode is half kVt. So 3 by 2 kVt. Similarly, rotational, this is an non-linear molecule, so three modes will be there. So again, it is 3 by kVt. So it is again 3 by 2 kVt. Now, E vibrational, number of modes we can find out. To total number of modes will be 3n N is here, 4, 1, 2, 3, 4, 4 atoms are there. So eventually it is 12. So EV will be, number of modes will be 3n means 12 minus 6. 6 are already used. Now it will be either KB. There I have to already discuss this, that what was that? The energy of the each vibrational modes depends on the temperature. Okay. In case of high temperature, it is 1 kBT. In room temperature, energy of each mode is 0.2 kBT. And at very low temperature, it is 0 kBT. So if it is high temperature, let's say, so it will be this. So it is 6 kBT. So total E or U will be 3 by 2 kBT from translational, 3 by 2 kBT from rotational, and 6 kBT from our vibrational. So it is eventually 9 kBT. Hence, del U del T V is 9 kB. This is for only one molecule. Okay. Now we have to calculate it for. So that's why it's better to write as U is internal energy equals to num Na. Then it's better. So we can write this is E. This is E. This is energy for one molecule, and U will be energy for Na number, Avogadro number of molecule, that will be N kBT Na. Now we know Kb into Na is R, so 9 RT. So it's now direct that Cv will be del U del dV, which is 9. Okay. Yes. Question number 4. In which option 1 minute. Okay. So in which option all are bosons? Options are electron, photon, nucleus of H2. Just I'm writing this. Okay. Nucleus I'm not writing. This means the nucleus of sodium and nucleus of oxygen, photon, nucleus of H2, again nucleus of Fe, nucleus of OE. Third one is proton, nucleus of hydrogen, nucleus of sodium, sodium 11, nucleus of oxygen, photon, nucleus of hydrogen. Okay, these are the options. We know that electrons, proton having the half integral spins, these are fermion, right? Bosons means having the integral spin. Bosons essentially have the full integral. Sorry, let me write it. full, um, okay, let me write it. Bosons should have the multiple of integral spin. Means 1, 2, 0, 3. These are okay. If spin is, let's say, I, if I is the spin, then eventually it will be Ni. Okay, like this. You can write. And fermion, we know this will be the half integral spin. For fermion, okay, which means half, 3 by 2, 5 by 2, this. So now we know for electron, proton, these are all fermion having the spin half. So essentially, you can directly eliminate this option because electron is there, this option, proton is there. So eventually these two options are left. Now you can directly see that these three are common. Only here is oxygen 18 and here is oxygen 17. That we have to now look at, consider. Okay, so oxygen 8, 18. This means there is 8 proton because we are considering the nucleus. I have not written it, but uh, one case I have written the nucleus of this, right? So 8 proton and 10 neutron. And here it is 8 proton, 9 neutron. Okay, so 8 proton in both cases there is 8 proton, and 8 proton means these are all paired. Okay, so if all protons are paired, that means this eventually the spin, how much spin will be there, that we can say. Each proton has the spin half, or let me write it. Consider this proton as electrons, and now you can do 8 protons means again it will be 1s2, 2s2, 2p4. Okay, so and 10 neutrons will be 1s2, 2s2, 2p6, like this. Okay, uh, similarly here as well. So eventually you can see that here it is 1s2, 2s2. It is not directly like this. Just for understanding, I'm considering like electron. 2p4, this is same, but here it is 2p5. So you can think like that. If this is a even number, that means these are paired. There are 8 protons, that means these are paired, means all protons are paired. All protons are paired means uh, there must be 4 up proton, 4 down proton. Okay, so what will be the total spin? Then 4 into half plus 4 into minus half, eventually 0. Similarly for here, 10 neutrons means 5 up neutron, 5 down neutron. So what will be the total spin? 5 into half plus 5 into minus half. So eventually it is 0. But in case of 9, 5 up neutron, 4 down neutron, or the vice versa, we don't know. So let me correct it, even not correct it, make it general. Plus minus, plus minus. Okay. Okay, so that means you can see it will be 5 into half plus 5 into minus half. Sorry, 4 into minus half. So it eventually half. So you can see that this is our fermion. This nucleus is a fermionic nucleus, but this nucleus is a bosonic nucleus. So this will be our correct option. Okay. Now this is our question number 4. Question number 5. 5 gram of ice at 200 Kelvin is added to 30 gram of water. Check whether this recording is going on enough because it's obvious. Oh, it's stuck. Okay. Water in thermally insulated container. What is the final temperatures? What is the final temperature given? Okay, the information given, del H fusion of ice at 200 Kelvin, that is 300 joule per gram, and average specific heat capacity of liquid water is 4 joule per Kelvin gram inverse. Okay, so what they have given, the 5 gram of ice. Okay, there is some water. There was some water in, the temperature of water was 300 Kelvin, and this is our 30 gram, and we have added some ice, temperature 200 Kelvin, and the weight is 5 gram. Obviously, then it will be equilibrate. Okay, it will be equilibrate to some temperature, let's say T. So for water, change in temperature del T is T minus 300. Okay, for ice, change in temperature is it was 200 Kelvin. Now when this is added, let's say you are adding ice in the water, so from here you can say it must be less than 300 Kelvin and greater than 200 Kelvin, right? Because it's ice is cold, ice is much colder than the water, ice is the temperature of ice is 200 Kelvin and 300 Kelvin. You know when these are adding, the average temperature, equilibrium temperature will be in between. So you can write it. So it means the temperature of water is decreasing and the temperature of ice will be increased. So that's why you should write it like 300 minus T. Okay. Otherwise, you have to use the mod. That's also you can do. Okay. So this will be the del T. This is del T for water, del T for ice. So, okay. Again, you have to think that again ice has converted to water. Okay. If you are just adding instead of ice, if there is a water of 200 Kelvin, then the thing will be different because here you are adding ice, not water. So ice has to melt in the water into the water. So that means ice will be converted into water. So ice will be melting. So we have to also account that heat of fusion that is already provided here. This is 300 joule per gram. This heat also released by the of this amount of heat to melt in the water. Let me clear it. This ice, 5 gram of ice, also melt into water. For that, he must need some heat. That heat also provided by the that heat. Where it will become? It will become from the bucket of water. Okay. So eventually, so now bucket of water, how much heat that losing that? Uh, First is this, which will be 30 grams, right? Yes. So we can write it heat gained by ice equals to heat lost by hot water. Okay. So how much amount of heat gained by the ice? First is M. This is given, right? 300. 1 minute. What is del H is okay. Okay, heat capacity is also there. Heat capacity of water is 4. No, heat capacity will not be changed due to the phase transition. So for ice and water, heat capacity is same. So M, heat capacity is C del T. This amount of heat and plus the ice has to melt into the water. So that amount of heat also you have to consider. That means that is del H fusion equals to amount of water MW, let's say it is MIC del T W. This we have to just okay. So this is 5 gram. C is given 4 joule per Kelvin per gram inverse. So this is for 1 gram. So it is joule per Kelvin per gram inverse into del T. This is already we have written down, right? That is T minus 200 plus del H fusion. Del H fusion is 5 gram into 3. Okay, yes, again, this is given 300 joule per gram. So eventually you have to multiply it with the 5 gram. Okay. And in the right hand side, it is 30 gram of water having the same heat capacity, but here it is 300 minus T. So it is Joule goes away. Here they are Kelvin. Kelvin. Similarly, gram will be cancel out. Okay. So unit is 20 into T minus 200 joule plus 1500 joule equals to 120 300 minus T joule. So it can be written as, now ignoring the joule, this is just unit. Okay. Or you can write it. Okay. Now again, if you divided it by 2, then it is 6, it is 75. To 75. Okay. I think this is correct. Let me check. If it is 275, then it is 75 into 20.
Yes, sir, it is correct. It is
Is correct, no? Okay. So it was question number 5. Okay. Okay, question number 6. 5 identifiable particles are distributed in 3 non-degenerate levels. With energies 0, E, and 2E. The most probable distribution for a total energy 3e would be. Okay. So now five identifiable particles. Identifiable means you can identify. So it's clearly meaning that the particles are classical particles. Means you can identify, distinguish the particles. If these are the quantum mechanical particles, then you can't do that. So eventually it is classical particles, means you have to consider the Maxwell-Boltzmann statistics here. So now there are three energy levels: 0, epsilon, and 2 epsilon. Now total energy should be 3 epsilon or 3. You have five particles. So if we, how many orientation will be there? That you have to find out. Number of types of orientation. So one maybe one particle is here, one is here, and rest of the three are here. Then the total energy will be eventually 3 into 0 plus 1 into 2 epsilon plus 1 into epsilon. So eventually it is 3 epsilon. Okay, so this is the one orientation. You can write it like 3, 1, 1. This is a possible case. Or, or, mm, it may be 3 epsilon, it should be. Total energy should be 3 epsilon. Okay, you have to keep the 2 here. Then this can be another possibility. Here it is also 3 epsilon. So occupation number is 2, 3, 0. Okay, one particle you can't keep in 0 state. So that you forgot. What can be there was 4 particle you can't put, because you have, if you put 4 particles, then you will have only one left, and there is no 3 epsilon as level, so that you can't. 5 you also can't. So I think these two are possibilities. You just think like that. Let's say first you put one particle in 0 energy state 0, then you have 4 particles, and you have to make the overall energy 3 epsilon. You can't make it. It will be always greater than 3 epsilon. So that condition is not possible. Next is, now you can put 2 particles in 0 energy state, like in this case. So now you have 3 particles and you have to make energy level 3 epsilon. Then only you can do that. 3 particles in the energy level epsilon. Then the total energy will be 3 epsilon. Otherwise, there is no other option in this category, in this case. Now in third case, you can put 3 particles in the ground state, 0 energy level. So now you have 2 particles in your hand. You have to make the total energy 3 epsilon. So this is only the probability. You can't do other thing. And if you put 4 particles in 0 energy level, then you can't make it is 3 epsilon. It may be maximally 2 epsilon. So only two possibilities are there. Okay, now you know how you can calculate the microstate under this 311, this orientation. It will be 5 factorial, but 3 factorial, 1 factorial, 1 factorial. So it is eventually be 20. And in this case, it is 230. So it is 5 factorial by 2 factorial into 3 factorial into 0 factorial. So it is 10. Okay. Yes, correct. So 10 and 2, 1, 2 can't be right. Hmm. So the maximum most probable state is this one. So this will be most probable distribution. Okay, so this is our question number 7. The 6. Now question number 7. The temperature of 72 gram of water is raised from 30 degree centigrade to 80 degree centigrade at constant pressure. The change in the enthalpy of the system given CPM of water is 50 joule per Kelvin mole inverse. Okay, so we have water, 72 gram of water at 30 degree. Now we are increasing the temperature to 80 degree, keeping pressure constant. The change in the enthalpy you have to calculate. Okay, so how we can do that? dH equals to, du plus pdv plus vdp, correct? And du is essentially d cross q minus pdv. If you put, then you obtain dH equals to d cross q plus vdp. At constant pressure, it is just d cross q, correct? So uh, again, CPM, what is CPM? CPM is d cross q dt at constant pressure for 1 mole. M is for 1 mole, molar. Okay, so you can write it del H del T, as it is constant pressure, you can write it. So this is the case. Okay, so del H or dH is eventually CPM dt. So del H, dH, if you integrate it, so del H, so it will be CPM, that is a constant. This is for, you have to keep in mind, this is for 1 mole. You are integrating in terms of temperature, but mole is there already. So this H is still H bar, mole for 1 mole, del T. So what is CPM? That is given 50 joule per Kelvin mole inverse. And what is del T? 80 minus 30 Kelvin, because we know the difference in centigrade is equals to difference Kelvin. So Kelvin will be cancelled out. Clear, it is 50-50. So this joule per mole for 1 mole. Now we have to calculate total H. Del H should be N del H bar. What is N? N will be now 72 gram divided by 18 gram. We know 18 gram oxygen, 18 gram water essentially means the 1 mole of water, and we are dealing with 72 gram of water. So this is our N and del H bar. So it will be 4 into joule per mole inverse. So eventually it is 10,000 joule per mole inverse. That essentially means 10 kilojoule per mole inverse. Okay, this is our question number 7. Okay, let me some more. Okay, we'll again continue after 1 minute. Let's see the recordings. Yes, this is going. Okay, now question number 8. Fermi function Fe, that is given 1 plus 1 by e to the power e minus ef divided by kbt plus 1, which essentially gives the probability of occupation of electron per energy state. Okay, function of E. So it essentially gives the okay, I'm coming. Let me just write down the question first. Then the probability of number of electrons at absolute temperature when E equals to F is. Okay, so first, what does the Fermi function mean? That Fe, FD, a Fermi distribution function or Fermi function. So this is eventually 1 by 1 plus exponential of E minus EF by kBT. It means the probability the probability of number of electrons, okay, in that particular energy level E. Okay, that is the case. That means that this is the probability of the occupancy or the filling probability, you can say. If Fe is 1, let's say, let me consider any energy level, this is energy level E. If Fe of that particular energy level is 1, that means there is a particle filled by, that means that energy level is filled by one particle. You know that These are fermions, so eventually there will be one particle or zero particle. Occupancy must be 0 or 1. If Fe is 1, Fe, a function of E, Fermi function is 1, that means that part energy level is occupied. There is a particle. Okay. If Fe is 0, that means that is totally vacant. Okay. That energy level is totally vacant. There is no particle. No particle is there. Now this Fe eventually can vary between 0 to 1, because particle can be 0 or 1, but probability of having a particle, that obviously a probability, so it can vary between 0 and 1. I think this is clear. So that's why this essentially signifies the probability of having particle in that energy level E. Correct. So one thing you can eventually can derive from here easily, when it will be 1, when F equals to 1, if you put F equals to 1, what will be the condition? It essentially means that 1 plus exponential E minus EF divided by kBT, that should be the 1. So this exponential E minus EF divided by kBT, this should be 0. So when this exponential term will be 0, that must be 0, no? So it will be 0 when the temperature is tends to 0, T. If T tends to 0, if T tends to 0 near absolute temperature, sorry, near absolute temperature, it must be blows up. So it will be infinite, but we need it 0. When it will be 0? If E equals to EF. Correct? If E equals to EF, then it will be 0, but it will be then exponential of 0 is 1. No, sorry. We need totally 0. That means this argument to be 1 by infinity, like these things. Yes, yes. Now, if t tends to infinity, t tends to 0, you can think now, if let's say E greater than EF, if E
Excuse me,
greater than
sir.
EF, yes,
If temperature tends to zero, then exponential function will be infinite.
infinite, but when if E greater than EF, then only. If
Okay, okay,
let's
sir.
say if E is less than EF, then you that will be minus infinite. So exponential of minus infinity is 0.
Zero, yes, sir.
Okay, that's why I'm
Okay,
writing if t tends to 0 and E is less than EF, then it will be 0. That this is the condition. Okay, so from here you can say when it will occur, that T must be tends to 0 and E must be less than EF, then it will be. Similarly, you can do when F is 0 means, from here you can do this is a definition of Fe. So you can check. Similarly, you can check if just T tends to 0 and E is greater than EF, then it will be 0. Just you put, then it will exponential this term, this argument will be infinite, as you say. So it exponential of infinite is infinite. So this term will be infinite, and Fe is 1 by this term. So 1 by infinite is 0, like this. So in that case, it will be Fe will be 0. Okay. But the one interesting case that is important when E equals to EF, and obviously T is tends to 0. Then you can check. Now this we must do. Then if this is, then exponential of E minus EF by T, you can check it is independent of temperature even. Temperature is not equal to be tends to 0. Then you can see that if this is case, this is eventually exponential of 0. That means this will be 1. So if this is 1, so now Fe equals to EF. So you can, so it will be 1 by 1 plus 1. So it is half. So means the probability is 50% to be occupied of that energy state, like this. So if you draw it, if you plot it, then it will be very clear. Let this is Fe and it is E, and here let's say EF. So until EF, that means E is less than EF. That means then this will be 1. That means the states are fully occupied. Let's say this is 1. Okay. And here this will be totally 0. Just there will be a jump, step function like behavior. And at EF equals to, this will be half. Okay. So this is the case. This will be sudden jump. Means you can think this is our plot, but the picture, the theoretical picture, how it will look like. Let's say there are various energy state. These are the energy levels. Okay. Somewhere there is, this is, let's say, EF. So the energy levels below EF, this means these energy levels are totally occupied, right? That means these energy levels are totally occupied. In each energy level, there is one particle. Totally occupied means that because occupancy may be either 0 or 1, so each energy level has one particle. Here, if each energy levels are vacant and the occupancy of this part energy level is half. So this energy level is called Fermi energy level, EF, and this is eventually is actually EF is mu, chemical potential. When T tends to 0, this EF is mu. Okay, that's why the Fermi function is eventually reduced to 1 plus exponential of beta into epsilon minus mu, the chemical potential. Beta is 1 by kBt. Okay, so this was asked, this is half. The probability will be half. The probability of number E equals to EF. So it is half. Okay, this is our question number 8. Question number 9. Okay. The value of molar heat capacity at constant volume will be. Okay, it's very, very easy question. Okay. Molar heat capacity, constant volume means CV. What will be the value of CV? You know, 3R for molar heat capacity for 1 mole of gas. It's just 3R. It's nothing to do. So now just we have to put 3 into R. Okay, the in unit. Okay, unit they have asked. Okay, will be in calorie mole inverse degree inverse in this unit. Okay, stick. Okay, so means degree inverse is Kelvin inverse. Degree centigrade they have not mentioned. So you can think this is as Kelvin inverse. So it is 3R. R just R we have to find out value of R. R is 0.082 calorie mole inverse Kelvin inverse. So it is 0.082. So it is 0.246 calorie mole inverse Kelvin inverse. Now, if they ask in degree centigrade inverse, then what will be the case? That must be important. So this is R, right? So you can write RT is eventually 0.82 calorie mole inverse. Okay, you don't know T, so T will be there. So into T Kelvin, T Kelvin. Okay, so RT. Okay, so this is our unit. Now, if you want to convert it from the Kelvin to degree centigrade, then how you can convert? So that is important, I think. But as long as this is considered as degree inverse, you can replace Kelvin inverse or degree inverse directly. If it is centigrade inverse, then it's not trivial. You have to then convert it, but this is not necessary because everything is in the Kelvin unit. Okay, so this will be our answer. This is a trivial question. Okay, now going to this is important. Okay, let's consider two identical particles have to be distributed in three energy levels. The ratio of the probability that the two particles can occupy two particle not can occupy same state to the probability that the two particle occupy different states for both Einstein statistics or both Einstein and let's say FD state. Okay, so there are three energy levels and you have two identical particles that essentially signify these are the quantum mechanical particle, right? So now that may be bosonic or maybe fermionic. So we have to find out the ratio of probabilities, two probabilities. In first probability, the probability of the two particles in the same state and the probability of the two particles occupying different states. So first, the probability of particle in same state, let's say this is P, same state that we have to find out divided by P different. This ratio we have to find out for both Bose-Einstein distribution, considering the particles are bosonic, and this fermionic. Okay. One thing also you have to keep in mind that PS plus PB should be equals to 1. Okay. Because total probability that is. Now for bosonic case, two particles Two particles are there in three energy states. So what will be the combinations? Let me draw. First, let's say in the same energy state. So mm, this is one. This there is no other possibilities because particles are same. So there are only three distribution, right? Three microstates. Okay. And in different, this may be one, this and this. There is no other. Is anything possible? Two particles that should be in different states. So these threes are possible again. So again there will be three microstate. So total six microstates, right? So what will be PS? That is 3 by 6. So that is half. PD, that is also 3 by 6. So that is half. So PS by PD for Bose Einstein, that is 1. Clear? Now for Fermi-Dirac, it's very easy. For Fermi-Dirac, we know PS is 0, right? Because two particles can't be in the same state. So there are only these three possibilities will be there. So eventually PD will be 1. 3 by 3, that will be 1. So PS by PD for Fermi-Dirac will be 0. Okay. Now question number 10 it was. Okay. Now not. So you said asked me this question, why glass is described as liquid, crystal or solid solution? Mm, that actually I don't know. I know that glass is actually a crystal, but there is some viscous thing is there. So you can think glass as a very uh, solid solution, but having a very high viscosity like this. Uh, Probably there will be some justification from the phase diagram from your question. It seems to be, but I don't know it correctly, so I have to know. Then I will say it. Okay. Next question you said this is correct. Why the helium gas? Let me write it. Then I will discuss. This is purely in discussion. Why helium gas cannot be solidified? Okay. Solidified, we know that gas to liquid to solid, right? Now, in gas, if you are considering the gas molecules, the intermolecular space is very high for gas molecules, right? Uh, when you are converting that gas to liquids, essentially the interaction will be increased. In solid, it is very well packed like this. Means how do you convert gas to liquid? If you think in terms of water, let's say water vapor to water, you have to decrease the temperature. When you decrease the temperature, essentially there are two things is there in gas molecules. One is molecular interaction or molecular attraction, you can say, and another one is thermal energy, right? This molecular attraction is very, very less than thermal energy in gas. That's why the molecules are free to move, and that is why the density of gas is very less. You know this thing. This is the feature of gas. Now, when you decrease the temperature, this thermal energy essentially decreased. This depends on temperature. So when that is decreased, then this molecular attraction and thermal energy, when become comparable, then it will form the liquid. And when it is comparable, then you can convert it. If you again decrease the temperature, it will orientate, and due to the asymmetry, it will form a liquid structure. Similarly, if you again decrease the temperature, then again molecular attraction will then much greater than the thermal energy, and it will be solid. This is the general prescription. But in case of helium, this helium is we know this is a inert gas, right? That means in helium gas molecules, there is no attraction or repulsion. There may be very uh, light attraction. The London force is there, very that is due to the just mass of things, but that is not sufficient to solidify that. You can decrease the temperature even, you can decrease the temperature, but never you can achieve this condition, because this molecular attraction is very less in case of uh, helium gas, because the helium gas is eventually an inert gas, right? So that's why you can't achieve this condition anyway. So that's why it will be not solidified. Okay, this is a theoretical argument. Okay, is this clear?
Yes, sir.
So, okay. Hmm. Okay, question number 12. A sample of an ideal gas with initial pressure P and volume V is taken through an isothermal expansion process. During which the change in entropy is to be delta S. If the universal gas constant is R, then the work done by the gas will be. Check recording is going on. Okay, so ideal gas, first the initial pressure is P and volume V. Now expanding isothermally, and the entropy change is del S. Gas constant is R. Work done we have to calculate. Correct. Now, how you can calculate work done? We know du equals to d cross q minus d cross w, right? And d cross w is, mm, sorry, pdv minus pdv. So you can write du is equal to d cross q minus pdv. This is work done eventually. So this work done we have to calculate. So d cross q is du minus d cross w. We know du is essentially cv Yes.
Excuse me, sir.
Uh,
Some confusion regarding the last question.
mhm.
If we consider ideal gas in place of helium, can
Yes.
happen with the same thing?
Yes, exactly.
Can it happen?
Exactly. Ideal gas, in case of ideal gas, there is no interaction. In helium gas, there may be some interaction because helium gas is an inert gas, close to ideal gas. Ideal gas does not have any kind of interaction.
Yes, sir. Now it is clear.
So, in case of ideal gas, you can liquefy them. Okay.
Okay.
Solidify is far away because to liquefy, you need some interaction. Otherwise, why that molecule will be close together?
Okay, sir. Thank you, sir.
That you can think in case of Bose gas, what happened in case of Bose gas, there is some uh, when you decrease the temperature very close tends to zero, that Bose-Einstein condensation occurs, na, that volume increases suddenly after a certain temperature very close to zero. That's also due to some kind of repulsion. That's actually due to the Bose-Einstein statistics. To liquefy or solidify, you must have some kind of interaction.
Yes, sir.
So this is CVDT. So and this is isothermal process. So dt is 0. So du is also 0. So you can write it d equals to minus d cross q. So it is minus pds. Okay. Now you have what we have to find out. Uh, the work done by the gas. Correct. Now we have to just integrate it isothermally. So it is del w or w, that will be minus t. I think there must not minus will not be there. I don't know. Yes, this, because there are two kind of nomenclature, right? One is IPSC and another one. So this confusion will always be there. Hmm. Du minus PdV. So d equal to dA minus, yes, now it's correct, I think. So it is T delta S. Now what is T? These are ideal gas. This is ideal gas. So you can write at initial state it was PV equals to nRT. So you can write T equals to PV by nR. So it will be P del S by. Now question number 15. Okay. Using the Fermi function that we have already known. evaluate the temperature at which there is 1% probability that a state with an energy 0.5 electron volt above the Fermi energy, okay, will be occupied by an okay. Fermi function definition we know. Evaluate the temperature at which there is a 1% probability. Okay, okay. Means this discussion we know. This is at t tends to 0, correct? You have to keep in mind this is t tends to 0. This will be half independent of temperature, but this is all occupied, unoccupied. This purely depends on t tends to 0. So now they are saying that above Fermi energy, just 0.5 electron volt above, let's say this is our Fermi energy, EF, just above this state, 0.5 electron volt plus EF plus 0.5 electron volt in this state. If it is t tends to 0, then you can directly write down that in t tends to 0, it will be 0. But we have to find out the temperature for which it will not be 0, it will be just 1%. That we have to find out. Very good question. Let us try. Okay, so now let's say this energy is E. So Fe now is 1 by 1 plus exponential of E minus EF divided by KBT. This is 1%. 1% means 1 by 100. So 0.01. So you can write 1 plus this is 100. 1 by yes. So this will be 100. It will be 99. Okay. So we have to take log in both sides. Correct. So from here the temperature you can find out. This will be E minus EF to KB ln 99. Is their value ln 99? Okay. So what is E minus EF? E minus EF is given 0.5 electron volt, right? This is just 0.5 electron volt above divided by KB into ln 99 is 4.59. This is just a number. So it is 0.5 into 1.6 into 10 to the power minus 19 joule, and KB is 1.38 into 10 to the power minus 23 joule per Kelvin into 4.5. So it is eventually 1.6 into 0.5 divided by 1.38, 4.59 into 10 to the power 4 Kelvin. So this will be, let me do it. So it is 1.6 into 0.5 divided by 1.38. So it is 0.1262 to 10 to the power 4 Kelvin. So it is 1262.9 Kelvin eventually. So this will be the temperature. Okay. At this temperature, there will be just 1% probability of finding a fermionic particle in the 0.5 electron volt above the energy of the Fermi level. Okay. So now question number 14. Okay. Again, a Fermi function. Consider a gas made up of two identical particles. Again, okay. Suppose that each particle can be in one of the four possible quantum state. It can be in one of the four possible quantum states. In case of every statistics, what will be the probability of having both particles in the same state? It's direct zero, right? Because if the statistics both particles in the same state, it is not possible. This information is totally waste. Nothing. Okay, directly you can do. Just waste of time. This is just zero. 50. Let's define question. A three-level systems of n atoms with energies E equals to minus E naught, 0, and E naught is in thermal equilibrium at temperature T. Let beta equals to kBT inverse. if beta E naught is 2, the probability of finding the system in the level E equals to 0 is okay. Okay, so there are three energy levels: minus epsilon E0, 0, and E0. Okay, and the temperature is T and beta is 1 by kBT. These are known to us. Okay, so beta E0 is also given, that is 2. Okay, now the probability of finding. Okay, what will be the probability of finding of energy level? This is let's say E1, E2, or epsilon 1, epsilon 2, epsilon 3. Okay, so we have to find out the probability of E2, is P2. We know this is just e to the power minus beta epsilon 2 divided by Q. Q is our partition function. So it is e to the power minus beta epsilon 2 divided by sum over j e to the power minus beta epsilon j equals to 1 to 3. Correct. Now epsilon 2 is 0. So you can directly write it 1 by sum over j e to the power minus beta epsilon j. So what it will be e to the power minus beta epsilon 1 plus e to the power minus beta epsilon 2 plus e to the power minus beta epsilon 3. Just now put the value. Epsilon 1 is minus E0. So e to the power beta E0, it is 1. It is e to the power minus beta E0. So this is the case. Now you have to use, so you can write, so what will be the P2? 1 plus e to the power minus beta E0 plus e to the power beta E0 inverse. So you can write it 1 plus cos hyperbolic of beta E0 to the power minus 1. Because the definition of cos hyperbolic function, cos hyperbolic of x is e to the power x plus e to the power minus x by 2. So eventually that will get. Okay. Now you know beta epsilon 0 value is given as 2 as well. So it will be, so P of 0, P of E equals to 0 is eventually 1 plus 2 cos hyperbolic 2 inverse. Okay, that's 15. So this is our second last question. That we want to see. Cp greater than Cv, this we know, where Cp is our heat of transfer constant pressure, Cv constant volume we know, because of because at constant pressure there are four options. First one is the attraction between molecules is larger. Second, the coefficient of expansion differs. Third, work is done by expanding the gas. The fourth is none of the above. So it is clear this should be the correct option because we know the C, this we have already discussed, right, in one class, that we have to increase. What is the definition? CV is du or dq dt at constant volume. We have to increase 1 degree temperature, for which the amount of heat required is CV. That is the definition of CV, the amount of it required to increase the temperature by 1 degree at constant volume. And CP is just the constant pressure. So in case of when the volume is constant, you are giving the heat. You want to increase the temperature. You want to increase you you want to have dT. So for dT, we must increase the du. Correct? Then only. So now you know from first law that d cross q is eventually du minus d cross w. Correct? You are giving heat that heat can be used in two way, du or d cross w. Plus d cross w. Two possibilities. Now when it is constant volume, this is PdV. So you can write it. Correct? So P that this work done will be zero. When the volume is zero, this will be zero. So eventually the amount of heat you are giving, the total amount of heat is essentially used to increase the internal energy. That means used to increase the temperature. But in case of constant pressure, some amount of heat is also used to do work done. Correct. So du will be in that case because q minus pdv some. So this amount of heat is used in work done. So that is not be utilized to increase the internal energy. So, but you want to increase some certain amount of du, then only the temperature will be increased by 1 degree. That's why you also add that extra amount of heat to compensate that work done. Then only the temperature will be increased by 1 degree. So work done is done by expanding the gas. That is the correct option. Now the last question. Okay. Again, Fermi function. Fermi function Fe, that is also known to us. Okay, there was, but here the Fermi function is different. 1 plus e to the power E minus EF by kBT. Instead of 1, there is 5. Okay, that gives the probability, the same definition of occupation. Just instead of 1, there is 5 of electron per energy state. Then same question. Then the probability of number of electrons, absolute temperature, when E is equal to EF is very rubbish. Same question. If you know, just you have to put E equals to EF. So it is just this is our function, right? So if E equal to EF, so it will be instead of 1 here is 5. So it is 5 plus 1. So it will be 1 by 6. Very stupid question. Okay. So this will be our final function. This will be the probability 1 by 6. Okay. So let me stop here today. Now, if you have any doubt regarding any question, then you can ask me.
In case of bonding, uh, metallic non-metals, this
In case
type
of
of formula conductivity of metals is greater than non-metals. This
yes,
formulation is it applicable regarding that type of properties?
yes, you can think like that because this is a property of electrons, right? Let me yes, okay. So now this you can think like this is just a band, right? Like this. Okay, this is totally occupied. Okay, and this is the that definition that valence band, conductance band, like these things, right? So it will eventually behave like a uh, conductor. Then if you increase the temperature, you can see that when you increase the temperature, the electron can jump to these levels. Then only the occupation will be greater than one. Now, in one question we discussed. So that's why this is just the thing like the electron is going to the valence band to the conduction band. Then the electrons will be in the conduction band. Then it will be a conductor. Like these things, you can think like that. This is a solid state condensed matter things, but that can also be discussed in terms of Fermi function because we know in conductivity electron is mainly responsible, and for electrons this Fermi energy is essentially be true. So in that way you also can think. Is it clear?
Okay, sir. Okay.
Okay. So in next week, probably our last class. So I will acquire all the rest of the questions and we'll discuss. And if you have any other question, two questions also left. You send me 5 questions, two are left. So I will discuss that too as well. So then in last class, in next class, we'll discuss the rest of the whole question. Okay. So let me
Thank you,
stop
sir.
stop presenting. We will meet again in the next class. Okay.